So in the last class, we formally introduced something named Cartesian tensors. And this index notation is very important for fluid mechanics because though at initial point, it looks like why we are complicating, but once we learn that formal language, it becomes so easy to express the mathematical quantities, what we come across in our fluid mechanics course. Especially like stress, in the last class we have discussed, saying something like force per unit area is okay for +2 level, but there is a problem in terms of orientation of the object or perhaps the direction in which force acts. And typically both force and areas are considered to be vectors. So division of vectors can be permitted as long as we are going to introduce higher rank tensor, which we call stress tensor. That is the place where we have stopped. And during our lectures, we will learn about something about the second rank tensors, what is contraction multiplication, how this force on a surface really orients, and what it means this Kronecker delta and alternating tensor. Then we will close this mathematical language using this Gauss theorem and Stokes theorem. That is the way we close our mass. Then we will again come back to our fluid mechanics to introduce stress, then decomposition of stress into pressure, isotropic parts, and shear stresses, then something about Euler-Lagrangian, and so on. We will go ahead. So just to recap the things for people who also missed the last class, let us consider if I have a rolling wheel where material is not present inside, completely hollow, but material is outside. If I would like to apply F is equal to ma, the typical way we apply is F is equal to ma on a center of mass. Once we identify center of mass, then I will be in a position to really say that mass is this much. Now it is having this entire object is having displacement, so I can calculate velocity, acceleration, and net forces, whatever it is acting on that, I can really balance it. But during 17th and 18th century, people had a difficulty when material is not present there. How I will be even in a position to really sense that F is equal to ma, I can really write it. Material exists only on the right red color portions. So what they try to do was pick any tiny part of that red color zone where material is present, introduce something like stress tensor at each and every point on the tube. In 2 dimensions, the entire periphery or perhaps the tiny disk. In 3 dimensions, that entire 3-dimensional cylindrical tube, whatever we have it. Now, once you have this stress definition at each and every point, suitably projecting on areas, one will be in a position to really calculate what is the total force acting on that system. So that equivalent total force one can really distribute on the center of mass. Then one can really use F is equal to ma. That is the place where we began. And then we try to define something like scalars. Basically, they can be represented by lowercase italic letters like A. They will always have some number like 1, 2, 5, 10, 5, 3, something like that. These are called scalars. They are defined maybe at each and every point in the space. For example, like density, if I am going to really say, maybe 3 kg per meter cube. It's a scalar defined in 3 dimensions. Maybe 10 coins, that's also a scalar. Maybe 5 kg mass is distributed, so that can also be scalar, and so on. And the typical notation, what we say is A, B, C, D, lowercase letters. And this kind of things, what we call tensor of rank 0. Now we just used a new word named tensor. The definition for this is tensor of rank 0. Similarly, then we try to argue something about vector. It has both magnitude and direction, maybe force, area, displacements, position vector, and so on, so kind of stuff. So direction usually we represent by arrow, magnitude by how much length it has. And typically the Cartesian coordinate vectors like E1, E2, E3, this kind of notation represents vectors. Maybe another displacement vector x bar, if I would like to really write it, I can really write it like x1 E1 plus x2 E2 plus x3 E3. This is the way I can really span or track something like a position vector. And typically in mass, this E1, E2, E3, these vectors are called basis vector, because once you have these basis vectors, any other vector on the plane, you can really span it or construct it. More like you can think of if it is something like a continuous system rather than just lines, but you want to calculate something like curves, you use Fourier series, something like sin x, sin 2x, sin 3x, sin 4x, cos x, cos 2x, cos 3x, cos 4x, and so on. These are basis functions through which any other function can be explained or expressed. So especially lines, points, we express it in terms of these basis vectors. Now the question really comes into picture. The summation plus sign for scalar 5 units plus 3 units is pretty straightforward. For vectors, we can, what it means like plus sign is bit ambiguity. Only component wise we will be in a position to add it. That means only scalar addition we usually bring into picture. So x1 e1 plus x2 e2 plus x3 e3 has bit more specific meaning compared to x1 plus x2. That formalism we would like to really generalize it for any kind of higher dimensional objects. Then we introduce something like tensors. More like example, what we have really picked is there is a plate, you apply a force. Now, if you are reorienting this force in 3 different directions, the results, the effect of this force on this plate will be completely different. So the same definition like stress per unit area completely differ in each of these cases. Though force is same, area is same. So one has that ambiguity which one has to really reconstruct it or rearrange it. Similarly, the second situation also we try to really look at it. Force might be in the same direction, but plate is slightly reoriented. Now again, stress per unit area may be completely different in this case because the result will be different. Though the value stress per unit area looks like same in all these cases, but the result is different. So one requires a unique way of defining what it means force per unit area for stress. So for that purpose, what we first defined is area is a vectorial quantity. Like in your calculus, you must have learned if there is a vector A bar and there is a vector B bar, A cross B also gives you a vector which gives you perpendicular direction for the plane what it is spanned by A and B bar. So area, you get it only by these 2 position vectors. If you are going to have this cross multiplication, you will be in a position to get what is the magnitude of that area and direction of that. That's the reason we call area is a vector. Now to define stress, what we try to do is force per area. So force is a vector, A bar is also a vector. We cannot straightforwardly do that because that operation is not permitted. We don't know what it means division. So for that purpose, what we try to do is let us introduce something like T bar. This is double bar means it's rank 2. That is the notation what we have followed. In case if I can do T dotting with A, the meaning is summation Tij Aj based on how many dimensions we have, 3 dimensions. If J is equal to 1, 2, 3, if we can do, we will be in a position to really define inner product. That means you have 3 by 3 matrix and there is 3 by 1 matrix. You would like to have certain kind of product so that this 3 by 3, 3 by 1 really condense into 3 by 1. The best operation what we can do is write it like Tij, Aj, apply summation over J is equal to 1, 2, 3. Then index Jj condenses and I index survives. That's the reason we denote F as Fi. The same thing, it doesn't matter summation we have seen in the programming last time. Instead of summation over J is equal to 1, 2, 3, if I have summation over I is equal to 1, 2, 3, the same result you will end up with. Only issue is at programming level, you cannot use Fj, but it's supposed to be Fi. Or Fi is supposed to be Fj. That is the only thing. In the loop, For I is equal to 1, 2, 3, for j is equal to 1, 2, 3, the summation remains same. That's also we have seen in the last class, which we try to really called as Einstein summation. Then we try to really explain that Fn is equal to, if I rewrite this entire story, this entire story like Tij Aj summation j is equal to 1, 2, 3 means T11 A1 plus T12 A2 plus T13 A3 and so on. That's also we try to look at. So at any higher dimension, if one would like to have P n by n, n by 1 matrix. Hello. Hello.
So yes, sir.
Yes. So any higher dimensional n by 1 vector we would like to have from n by m tensor and m by 1 tensor, the natural choice for is to go with inner product. So mm condenses and gives me n by 1. In case if I would like to really make it in that way, it's not necessary that always dot product we have to introduce. By dot product, you are actually condensing the information. There will always be other products. That's what we called in the last class dyadic products. Something like A is n by 1 vector or tensor of rank 1. So it has individual components A1, A2, A3 and so on AN. And similarly, B is equal to B1, B2, B3, Bm. Now I would like to construct a kind of product which increases A multiplied by B to higher dimension. The easiest choice what I can really think of is A bar B bar is AI Bj product I am going to calculate, where I is equal to 1, 2, 3, J also 1, 2, 3. Because there is no repetition of indices I or J, what we have to do is just right away fix I is equal to 1, change B1, B2, B3. So A1, B1, A1, B2, A1, B3, and so on, A1, Bm. Now J index is over. Now I index really comes into picture. So A2, B1, A2, B2, A3, B3, and so on, A2, Bm. Further increase the index of I. So it goes all the way to AN, B1, AN, B2, AN, B3, and so on, AN, Bm. This is one kind of product what we can get. This is the biggest product what one can really get it from n by 1 and m by 1 vectors. Maybe there might be other combinations of reducing the matrix. That's always be possible, but this is one kind of product. Now let us think of something like A dot B multiplied by C bar. I would like to first of all, what we are trying to do is we are learning this language. Once this language is bit clear, then showing any equations talking about that equation becomes easy. That quantification what we are trying to do. Now A bar dot B bar multiplied by C bar. Multiplied is nothing about dot product or cross product. It's just multiplication. So the place where this index notation really comes into rescue us is, now look at what it means. A dot bar B bar C bar. A dot B. So there is condensation I would like to really look at. So A vector is AI, B vector is Bj, C vector is Ck. Where I is equal to 1, 2, 3, J is equal to 1, 2, 3, C is equal to 1, 2, 3. Now because there is inner product A dot B, what I am going to do is on AB, I'm going to apply I is equal to 1, 2, 3, AI, BI, which is your traditional A1, B1 plus A2, B2 plus A3, B3 plus and so on. That's just at math level. What we are showing is summation I is equal to 1, 2, 3, AI, BI. Now the other vector, what is he spinning is Cj or Ck. It doesn't matter. So this, what you are seeing is there is a scalar multiplying different scalars of C, C1, C2, C3. So A dot B of C is summation AI, BI, Cj. And if I'm going to really represent in the expansion form, summation AI, BI, Cj is A1, B1 plus A2, B2 plus A3, B3 multiplying C1, C2, C3. The first biggest advantage in terms of going with this indicial notation is all the time you will handle only scalars. Your multiplication, your division, subtraction, sine function, cosine functions, complex notation, whatever, everything, we will be in a position to apply it only on scalars, and that is the biggest advantage for computers. At higher level of fluid mechanics courses, CFD, computers, when you are going to learn, doing calculus becomes so easy when we handle scalars rather than worrying about vectors or any other kind of thing. The indicial notation actually helps us in such a way that it helps us to handle only numbers, scalars. No more vectors, no more higher order quantities. Everything really condensed to such kind of beautiful form. Computers can so easily calculate this kind of things. So you can teach computers so easily to program them. We will see when we are going to handle these vector products. Okay, so basically in fluid mechanics or any higher sciences, before 19th century, people try to go with the Gibbs notation. Gibbs, Willard Gibbs, Josiah Willard Gibbs is beautiful physicist. He worked on thermodynamics, calculus, electromagnetics, and many kind of fields he has touched. He is a USA scientist. In fact, if you are going to Yale University, still his boss representing his contributions at that university. His phenomenal contribution, what he has done for thermodynamics, especially solidification, melting, material science, and so on, so kind of stuff. And usually the scientists, if they are good with science, they're usually good with maths also. This is the way it goes because the tool is very much required. And Gibbs has really contributed phenomenal for vector calculus. Before Gibbs, people try to use calculus, but handling this kind of velocity, acceleration, fluxes, electromagnetic fluxes, these kind of things are not that easy task. So he made a formalism in terms of introducing this notation, like vector means this, dot means inner, B means this, cross means this kind of notation he has developed. The notation, what we take it obvious during our plus two, like A cross B, A dot B, A means this, B means this, there should be I, J, K, all these things in some sense generalized, made more formal. I'm not saying that Gibbs has introduced, but Gibbs has collated all these things to really clarify the things and made it very simple. And that was the thing what really accelerated science in terms of this notation. That kind of notation, what we call as Gibbs notation. In 20th century, when people started realizing that this Gibbs notation has its inherent difficulties in terms of going for higher rank tensors, explaining stress and so on, so kind of stuff. So let us use other notation named indicial notation. So there is a person named Ricky, Christoph, this kind of many guys are there who try to simplify furthermore notation of Gibbs thing, because at Gibbs level you have to handle vectors. At indicial notation you handle only scalars by just giving something like A dot B C means AI BI CJ, everything scalar. So that kind of flexibility they have given, so that one can really go much better way for computer programming and so on. We will come back more. Something like a Gibbs notation, when you are handling, care is very much required. Whether you are really writing legally right or not. For example, like if I'm saying A dot B cross C, is it permitted? Hello, guys.
No, sir.
So A dot B cross C, is it permitted or not is always be big doubt. Now the question, whether I write it in this way or I write it in this way, which one is permitted?
Second one.
Second one is
Right?
Second
So
one.
depends. So depends on the pupil how they write it and so on. So kind of thing is so difficult to handle this. I just gave one simple example. When you really jump into maths and try to do that, there will be many vectors interacting with each other. You are going to simplify and so on. Even you just miss one of these parentheses, entire steps gone. The end of the result, it looks like non-trivial thing or stupid. It looks like just simple example itself. What we are trying to say is, no man, this is not permitted. This is permitted. That kind of ambiguity, this indicial notation actually avoid you. Why I'm saying is, here I need to really care about this. But look at this indicial notation. AI, BI, CJ, it's perfectly fine because these are scalars. They're multiplying with each other and CJ. So when I'm going to really vary J is equal to 1, 2, 3, definitely I am going to really get this vector only, but not something else. That kind of thing, what we will be in a position to really get. For example, later we will see that example. Okay, this example, specific example, we will look at it. And this is very much required for our fluid mechanics. Handling this little bit mass. So that's the thing what I was saying, something about advantages of this indicial notation. For example, let us look at this first example. A dot B dot C, is this correct? Any idea?
no, sir, it should not be correct.
Right, that's the thing what we are going to really see through simple indicial notation. Let us look at that. This looks very easy example. That's right. But what we are trying to learn is, can we really apply the formalism what we are learning even for the simple examples to see that? It looks like what is big deal about that? But once we learn that language, later we will see the advantage. Okay, let us look at what it means A dot B dot C. A dot B in indicial notation means summation I is equal to 1 to 3 AI Bj, where I is equal to j, or perhaps condensation I would like to apply. So summation 1 to 3 AI Bi. Now there is something like a dot C. That means once again I need to condense. Now when I have already AI Bi summation is a scalar, it's not anymore a vector tensor of rank 1. It doesn't have any index. Everything really condensed to just one variable. It doesn't have any variation of I is equal to 1 to 3 or j is equal to 1 to 3 kind of thing is not there. It's just one single number what we are ending up with, summation I is equal to 1 to 3 AI Bi. Whereas C bar has an index like Cj. Now you want to condense a single value with a big 3 elements, which is not possible. So in that sense, A dot B dot C is not permitted operation. Let us look at the second one. What about this? A bar dot T tensor of rank 2 dotting with D bar. Can you see my screen? Hello.
Sir, I am seeing some other portion.
How about this?
Yes, sir. It's okay.
A bar condensing a tensor of rank 2, again condensing on tensor of rank 2. This kind of thing we will see. That's the reason we are learning. Is it permitted, not permitted? For example, this T bar, second rank tensor, you might see stresses, you might see something like strains and so on, so kind of quantities. They might be interacting with each other and so on. Is it permitted, not permitted? Can anyone answer?
Permitted.
Permitted. Let us see. How do you know permitted or not? Did you calculate
Like
it
the
or
first
just
two will condense to a vector like thing,
okay?
and again
Fine.
the both will condense.
Wonderful. So let us look at step by step. Now A dot T dot D, I would like to really do. Now this parenthesis doesn't matter. Is up to you how you want to really put parenthesis also at indicial notation. Now let us look at what it means. A dot T. T is a second rank tensor. That means you will have indices I, J, where I varies from 1 to 3, J also varies 1 to 3. And A is also having 3 indices. Because of dot, A dot T means summation AI Tij, where A1 multiplied by T1 1 plus A1 multiplied by T1 2 and so on, so kind of stuff. Is this step clear to everyone? A dot T, the index notation what we have written. Is there any person having difficulty in terms of seeing A dot T means as summation AI Tij? Okay, none. So I think it is clear. Now dotting with D. Now let us look at what it means. So summation I is equal to 1 to 3 AI Tij. Dotting with D, it has new indices M comma N. Because it's a computer program, you don't have to really stick with I comma J. It can be M comma N. For M is equal to 1 to 3, for N is equal to 1 to 3, D of M comma N is some value and so on. Now I would like to really condense dot. That means already one summation is there which already condensed AI Tij. The index what we see for AI Tij is leftover index is J. Because when you sum on I is equal to 1 to 3, already I is different, gone, but J loop still exists like for I, J is equal to 1 to J is equal to 3. So you have a vector of 3 components and here dmn. But because there is a dot product, we have to condense one of the index like J is equal to M. That representation from the top step to bottom step, what we are doing is summation J is equal to 1 to 3, already internal part djn. Wonderful. So once the computer loop is done, what you end up is a just vector. Can you identify vector of what dimensions? Hello guys, am I audible? So A bar T second rank tensor dotting with again second rank tensor. What is the vector size? Can you tell me those dimensions by looking at this
3 into 1.
expression? Huh?
3 into 1.
3 into 1 or n by 1, right? Hello?
Yes.
Yes? Okay, fine, great. Now let us move on to the next step. So it is perfectly fine to have such kind of product A dot T dotting with D. Now, just to give you a feeling, this entire summation notation, if I am going to really write it, if I would like to really represent it in terms of computer language, basically A is AI, where I is equal to 1 to 3, A1, A2, A3, Tij, J is equal to 1 to 3 and I is equal to 1 to 3. This is the way we represent. Dij, again I is equal to 1 to 3, J is equal to 1 to 3. Now A dot T dot D, if I would like to calculate, which I am going to call B, then what I have to do? There is a loop for n is equal to 1 to 3. for j is equal to 1, 2, 3, for I is equal to 1, 2, 3, A, I, T, I, J starting with DJN. This is the thing what we have to really calculate. If I repeat that entire thing, then I will be in a position to really get A dot T dot D. That is the way you program it. Now think of such kind of stresses, strains, and so on, higher order quantities interacting, and you would like to really calculate using your CFD, the colorful pictures and so on, so kind of stuff. This product becomes so easy to manipulate. Later we will see that. So such kind of advantage it gives you. But if you are going to teach a computer, I bar, J bar, K bar, and something like higher dimensional quantities, it is not that easy. For example, like cross product, you might remember how to calculate it. Remember like I, J, K, something like you cross multiply and so on, so kind of thing. That kind of definitions, we cannot teach it to computer. This is the only way we can teach it to computers. And that's the reason this indicial notation becomes so popular at later stage. You understand what I'm trying to say? Something like if I want to teach A1, A2, A3 cross product B1, B2, B3, something like I, J, K. This is just two vectors cross product, but higher rank things we don't know. If I want to really teach it to computer, it's not that easy task, the way how you remember. Whereas this kind of simple loops is pretty easy to handle. Okay, fine. Let us move on if no queries. How about A cross B? The next step naturally comes into picture. Can you see A cross B?
Yes.
Hello?
Yes, sir.
So this A cross B, what we are saying, the red color, what we call Gibbs notation. Computer or indicial notation is epsilon ijk ai bj. What it means, we will shortly see. A vector is ai, B vector is bj. But if you are going to multiply with something named epsilon ijk, which usually we call alternation symbol or permutation tensor, then this cross product can be so easily handled. It looks like what all you require is little bit attention and patience for next 5 minutes so that it becomes easy. Once we learn that, we don't have to worry about it rest of the places. It becomes so easy. So epsilon ijk is more like your matrix only, but it has three values, either +1, -1, or 0. These are the only three values it takes. That means when you are going to teach it to a computer, you just initially define what is epsilon ijk. Once it is done, once you construct a loop, any A cross B, you just supply this is A, this is B, just calculate this, becomes so easy. That's the way this programs works. These three values we have to decide, +1, -1, 0, depends on whether it is how I, J, K values are oriented. First thing, any 1 to, so I, J, K values always ranges from 1, 2, and 3. I'm just showing something like a cyclic notation. If I am going to see something like epsilon 1, 2, 3, for example, epsilon 1, 2, 3, this kind of array element I'm going to see, where 1 followed by 2 followed by 3. That's what I'm going to show it in a cyclic way, like 1 arrow going to 2, going to 3, and again repeat. If that kind of way, or something like epsilon 2, 3, 1, are epsilon 3, 1, 2. Whenever I see such kind of thing, I'm going to replace that value by +1. So if I see any indices in a very cyclic way, 1, 2, 3, 2, 3, 1, 3, 2, 3, 1, 2, and so on, epsilon ijk value is +1. And all I, j, k values should not be equal to each other. Instead of that, any of one of these sign is reversed. 1, 2, 3. I would like to really go in that way. Instead of that, I'm going to see the first one as epsilon 1, 2, and 3 really comes into picture. So if I am going to see maybe 3, 2, either in that way, or I'm going to see something like epsilon. After 3, what I'm supposed to see is 1, but now I'm seeing 1 in this way. If that directional sense is flipped, that value becomes -1. Is this clear? Anywhere, if we are seeing for epsilon permutation symbol or alternative symbol, instead of 1, 2, 3, 2, 3, 1, 3, 1, 2, this kind of thing, there is a directional flip happens. Instead of 1, 2, 3, I saw 1, 3, 2. That means that epsilon value is -1. And again, all I, j, k should not be equal to each other in the loop. Is this step also clear?
So why are the diagrams like this? Wouldn't it be like anti-clockwise direction?
I will tell you why we are trying to do. Because A cross B, somehow our teachers told us like when you are going to really multiply, for example, let us look at it in this way. Now, can you tell me how to calculate the vector product A cross B? Just tell me whatever you learned in your previous classes.
Determinant.
Can you tell me?
Sir, here we will write A2 into B3 minus B2 into A3I.
So something like first you close this one, then calculate whatever this A2 B3 and B2 A3, right? Subtraction. Now I want to really facilitate the operation on computer. How will computer really knows? First you close this thing, first you do this and so on thing. And it should not be just for this product. It can be any generic cross product. Right now you are learning only for vectors, but tensorial kind of cross products I would like to really do, higher rank things. How will I teach to computer? For computer, you might really put that you first take 3 values, next 3 values. Now just write something like A2 B3 minus B2 A3. That is first element you will get. Second element comes like B1 A3 minus A1 B3 and so on. So kind of stuff. You can really do it for 3 components where only vector to vector kind of thing is there. But as you are go on learning that, you may have to really generalize that procedure. So how are you going to do that? For that purpose, cleverly what they have introduced is this epsilon ijk, where the +1 sign, -1 sign is whether you want to really go it in the forward direction or backward direction. That is the reason why we are actually introducing this permutation symbol. Fine. When we are going to really write that, then you will understand that what we are trying to do. But as of now, just take it for granted, as long as it is 1 followed by 2 followed by 3 and so on, so kind of stuff. In that way it happens, epsilon ijk value is +1. But whenever 1, 2, 3 disruption happen in terms of follow up, then that value is -1. Whenever any of I, j, k are equal, they are equal to each other, that value is 0. Whether I is equal to 0, but they are not equal to k, then 0. When I not equal to j, but j is equal to k, that value is 0. When I is equal to j is equal to k, that's value also 0, and so on. Something like, if I am going to really show example, epsilon 1, 2, 3 is equal to 1. Epsilon 2, 3, 1 also 1. Epsilon 3, 1, 2 is also 1. Because they are in the same direction. Whereas epsilon 1, 3, 2, instead of 1 followed by 2 and 3, we have a flip. That value is -1. Epsilon 2, 1, 3. 2 followed by 3 supposed to be there, but there is a flip. Value is -1. 3, 2, 1. After 3, there's supposed to be 1, then supposed to be 2, but there is a flip in direction -1. Any other combinations like epsilon 1, 1, 2, you start seeing in the computer program. Then that value is equal to 0 because they are equal at one point. Epsilon 1, 3, 3. These two indices are equal, so that value is equal to 0. Epsilon 1, 2, 2, 0. Epsilon 2, 1, 2, 0, and so on. Why we are teaching this way, or perhaps why we are going, is once you create at a program level what is epsilon, that will be there for any times, whatever might be your boundary condition, whatever might be your initial conditions, whatever complex products you would like to really construct. Once you teach a computer this is epsilon, you just call it by function. Now call epsilon, now multiply epsilon. It becomes so easy for the computer to handle it. Teaching it becomes easy once we program it. Okay. Now, what is the use of introducing that epsilon ijk? Now let us look at A cross B. A cross B, by definition, epsilon ijk ai bj, where summation supposed to be on I and j, repeated indexes and j. So a vector in the third dimension, k dimension, you will get it. The whole point of this epsilon ijk ai bj means summation I is equal to 1, 2, 3, summation j is equal to 1, 2, 3, epsilon ijk ai bj. So a vector of k dimensions, you will get it. Now, how we are going to really teach a computer in terms of cross product? Let us look at this program. The program is, let me highlight it. This part. Can you see yellow highlighted part? For k is equal to 1, 2, 3, for I is equal to 1, 2, 3, for j is equal to 1, 2, 3, summation supposed to be on ij. So epsilon, we are representing E, I, J, K, starring A, I, B, J, which is more like this one. Can you see this one? The cyan color highlighted portion. Double summation, I is equal to 1, 2, 3, J is equal to 1, 2, 3, epsilon ijk ai bj is written as epsilon ijk ai bj. Summation, double summation means I have to introduce something like a ck variable, ck plus epsilon ijk star ai bj. So for I is equal to 1, 2, 3, j is equal to 1, 2, 3, it go on add it as long as k is equal to 1. When k is equal to 2, you will calculate C2. When k is equal to 3, you will calculate C3. Once you teach Eijk, this cross product, you don't have to ask computer to remember. By just this simple loop, it will calculate. You might say that you just give me A1, B2, A3, B3, and so on, I will calculate. But if I'm going to ask you, for example, I do not have 3 by 1 vectors, but I have n by 1 vectors. How are you going to calculate A cross B? You understand my question? If I am going to give you A bar is equal to A1, A2, A3, A4, and so on, AN. Similarly, I am giving you B bar is equal to B1, B2, B3, B4, and so on, Bn. Can you tell me A cross B by your standard procedure?
Sir, it
If
will become an n cross n matrix, and according to
No,
the
no,
EF,
don't look at our indicial notation. What I'm asking is, in case the +2 knowledge of A cross B, like I, J, K, and writing A1, B2, and so on, how easy it is to write it or perhaps calculate it by our +2 way of looking at A cross B product. And if we go with indicial notation for computer, how easy it is to really generalize whatever might be the dimension of a vector. Can you see the advantage in doing that? Hello? I mean, okay, let me write it something like this. I, J, K, L, M, N, O, P, vectors and so on, it's going. Now I'm asking you A1, A2, A3, A4 and so on, so kind of stuff, AN, whatever. And B1, B2, B3, B4 and so on, so kind of stuff, Bn. Can you get me A cross B information? Huh? Is it possible? Is it not possible?
So by
Is it
plus
easy?
two
Is it
method, I think
difficult?
it's
Huh?
difficult.
Name
By
yourself.
plus two method, it's difficult. Sir, I'm
Name
Niranjan.
yourself. You are Niranjan. Okay, Niranjan, go ahead. Answer it.
So by plus two method, it is difficult, but I think we can just simply substitute these things in the above formula and change 3 to n.
Precisely. What you are saying is the one actually inspired these elders to really come up with more formal way of looking at the things. Whole point of applied mathematics is that whenever people really face difficulties, it's not that you have to only work on 3x1 kind of systems. It should be more general. For example, like stress. All the time we try to think about that only vectors is the end. But then people really run into trouble, like when vector division is not possible, there must be existing higher dimensional quantities. That kind of thing inspired them to really go for more formal approaches. When we go ahead with this kind of indicial notation, that kind of advantage, what we will really come up with. Though we say that computers are advantageous, people really thought about all these processes, even how to teach computers. That index notation, what we are trying to learn. Once we learn that, even the fluid mechanics becomes so easy to appreciate. Now let us look at, I just require 2 more minutes, I will close the session. Now what is EIJK? By this definition, we have already established the algorithm. Now computer, what it does is pretty straightforward and easy thing. Now look at when k is equal to 1, ck, I'm going to really look at. Is for computer is so easy. E111 plus star A1 B1 plus E112 A1 B2 plus E113 star A1 B3 plus and so on, so kind of stuff. Already computer knows this value is 0 because repeated index. This value also 0 because of repeated index. This value also 0 because of repeated index. This value also 0 repeated index. This value also repeated index. But this one value survives. E123 is 1 because of cyclic notation 123, which we already taught computer. What is E? Something like 3x3 matrix or n by m by p kind of matrix we already taught. It already stored those values. Now you just simply calculate what is this. It's so easy. So only this component really survives. Similarly, E131, E132, E133, these values become 0, this value also becomes 0. Only this component survives, E132, which is -1. So the entire C1 becomes A2B3 minus A3B2 based on your perception. Clear? In the same way, C2, C3, computer can so easily calculate it. That is the advantage what we are trying to see. Is that clear to everyone? Or having a
Yes, sir.
difficulty? My suggestion, see, math only comes by practice. My request to everyone, I already have shared the notes. Go line by line, step by step. It looks like why we are unnecessarily complicating the thing from our +2. But the advantage it is when you are going for higher studies and so on, so kind of stuff, or programming, teaching, R&D kind of thing, this formalism helps you a lot. And second thing, what you have to really do is open the textbook also, Kundu and Cohen, Fluid Mechanics. Chapter named Cartesian Tensors. Go through them. That math is very much essential and important also. And also, please go through the notes. We will again discuss if you have any queries. Once this permutation symbol is obvious, understood that, we can really go with Kronecker delta, what it means and so on. We require one more extra class or perhaps connecting class to close this math. Once this math up to Gauss divergence theorem is done, then we will really go ahead, try to understand Euler-Lagrangian stress tensors and so on. Is that fine, guys?